For our second example, suppose
the answer to the ultimate question of life, the universe, and everything is 42.
But you don't find this to be a particularly satisfying answer.
42?
In particular, some statisticians agree with you. So, they ask 12 randomly selected supercomputers, let's say the HAL 9000, the Allied Master Computer, and whoever else they can find, for an answer, and get the following totally not made-up dataset of 0, 10, 3.14, 7, 23, 40, 13, 29, 38, 2.72, 54, and 66. From there, at a level of significance of alpha is 5%, is there enough evidence to suggest the answer is not 42, treating it as a mean where we make the appropriate assumptions on top? Like I said, this one's a little bit lighter. Anyway, we want to make sure those conditions work. Like I said, making that assumption, or always making that assumption. I don't like trick questions generally, and thankfully, at least in this context, the book doesn't either. So from there, if we want to think about what our hypotheses are, well, it's going to follow the same sort of pattern that we're used to. Here, in this case, we are working from the idea that that mean of 42, and it's not good enough. It doesn't matter that deep thought says that's good enough. We say that the answer to the ultimate question of life, the universe, and everything probably isn't 42, and we're treating it as a mean for the sake of being able to test it in this way. That's our claim. So, we're comparing that to the apparent truth of what deep thought says, that the mean is 42. The answer is 42. Where that has the behavior of a null, and our claim has the unequal behavior of an alternative. Then from there, if we want to talk about things like our level of significance, why I drew a blank on that? Very basic, it's very important. I took the standard value here, alpha is 5%. 5% is very, very common. You'll see it a lot. And I'll pause 1 second here in terms of the process, just to say one other big indicator that what we're going to do here is something in terms of a t-test, is we're given a mean, and then we're given a data set, and basically nothing else to work with except for the value alpha. In practice, not just on the homework, but in general, if all you have that you're working from is a data set and a supposed mean that should fit it, that is the clearest indication you'll get that you should be working with the t-distribution. Because remember, the t-distribution is for when we really only know about our sample. And in this case, that's the vast majority of the information we have, so we want to use the t-distribution. Anyway, going from there, we want to get our degrees of freedom along with our t-score, where the degrees of freedom aren't so bad. Remember, that's 1 minus the sample size. So here we asked 12 computers, so df is going to be 11 and minus 1. Meanwhile, to get that t-score, well, it's going to take a little bit of doing. It's going to take a little bit of, let's say, arrangement to be able to get that mean and standard deviation out of there. So if you need to get those specifically, you can, but really what I'd recommend doing instead of pulling those out specifically and going through step by step is using the t-test computation in your calculator, where you just enter in the dataset as it is and have it run on the dataset, in which case it will spit out the numbers you need along with everything else, in particular, for us, the t-score and the p-value. Where if we want to get that t-score, because this is a two-tailed test, we will get that t is approximately plus or minus 2.893. Technically, it's the negative one, but because this is two-tailed, we can take both. And then from that, we'll have some flavor of distribution that we're working with, like so. And if we need to get the p-value, we can use the same sort of complementary things with TCGF, but remember, t-test gives us that number as well, so we're going to get the p-value here is approximately, in this case, again, about 1%, 0.146. I think I said this at the beginning in 7.1, I probably said it again in 7.2, and I'll say it again now. Usually, our p-values are going to be really small. They're going to be in the single digits, because otherwise it's just not a very interesting test. Although every now and then we will get really big numbers, big relatively is anything above 25%, but often it's not much of a decision if these are big to begin with, so usually they're going to be set up to make them small. Anyway, we have this p-value here, which, importantly for our purposes, is, again, less than alpha equals 5%. That's a better alpha than I've gotten on the last few. So, because alpha is bigger than our p-value, we're going to go on to our decision. We would again reject the null hypothesis. So sorry, deep thought.
Geez, it's 42.
But it looks like you're not quite on the right track here for the answers to that ultimate question. And as a result, we could say something to the effect of, there is enough evidence to support the claim that the answer to the ultimate question of life, the universe, and everything is not 42 at level of significance alpha equals 5%. Where again, let's just remind ourselves that when we're talking about this p-value, what that represents is that there's about a 1% chance that our data set shook out the way it did if we assume that that mean there is accurate. If we assume that the answer, the ultimate question, is actually 42, that 1% in the context of a 5% chance is enough to say that something's probably wrong with the answer we were given. Maybe it's time we look for a new one. That's how those p-values work, just as a reminder. When you see these things a few times, it's easy to forget the context of what it is you're actually trying to do. Anyway, that's our examples for p-values. We'll finish this section off before moving on to 7.4 with one on the critical value approach.